Welcome to the first submodule of 4 on Drillstring Design. We'll explore influences, industry standards, mechanical properties, common failure mechanisms, and design factors. The aim is to establish a foundation for safe, effective drill string planning. In this submodule, we focus on building a clear understanding of the drill string design process. Specifically, we will examine the major influences that act on a drill string during operations, from geological loading to operational stresses. We will also study how failure mechanisms occur, particularly in relation to overload and fatigue, and consider how design factors are applied in real drilling environments. The intent is not only to provide definitions, but also to highlight how these issues appear on the rig floor and how they affect safety, performance, and cost. The objective is to move beyond simple theory and into applied engineering practice. Other objectives such as advanced torque and drag modeling and dynamic loading analysis will be covered in subsequent submodules. At this stage, we are concerned with developing an appreciation of how design choices impact drilling outcomes. By the end of this submodule, you should understand how to identify the main forces acting on a drill string, why industry standards are applied, and how safety factors are chosen to reduce the risk of costly or dangerous failures. This session therefore establishes the framework for later, more detailed analysis. There are conflicting needs in the 4 areas of the objectives, and the designer's choices will be heavily influenced by other factors such as rig capabilities, geologic factors, cost, and availability. Drill string design does not occur in isolation. It is shaped by a combination of geological and operational factors. Geological influences include lithology, pore pressure, fracture gradients, and well trajectory. For example, extended reach wells impose much greater torque and drag than vertical wells, demanding stronger tubulars with higher fatigue resistance. Operational influences arise from tripping speeds, rotary speed, and weight on bit. Excessive rotary speed can accelerate fatigue, while high tripping rates may induce surge and swab pressures that place additional stress on the string. Environmental factors including temperature, corrosion potential, and the type of drilling fluid also impact performance. According to Mitchell and Miska, 2011, successful design begins with accurately anticipating these loads and their interactions. By integrating geological forecasts with operational planning, engineers can select pipe grades, tool joints, and bottom hole assemblies that withstand the expected stresses. Failure to account for these influences often results in costly incidents such as stuck pipe, fatigue cracking, or catastrophic parting of the string. Thus, understanding influences is the first and most important step in reliable drill string design. Drill string design is underpinned by industry standards that provide both baseline requirements and best practices. The American Petroleum Institute, or API, sets minimum specifications for drill pipe, collars, and connections, including dimensional tolerances, steel grades, and mechanical properties. These standards ensure uniformity and compatibility across the global industry. However, API specifications alone are not enough to guarantee reliability. That's why the DS1 standard was introduced, offering detailed inspection, design, and operational guidelines for drill strings. DS1 emphasizes failure prevention through improved inspection criteria, fatigue management, and operational discipline. Together, these references form the backbone of modern design. They enable engineers to not only specify the requirements for materials, but also to establish procedures for testing, inspection, and field use. One of the most practical approaches in drill string design is to break the well into hole sections and design each part of the string accordingly. Shallow hole sections often face challenges of buckling, bending, and vibration. In these intervals, stiff drill collars and stabilizers are chosen to minimize stress. In contrast, deeper hole sections experience greater axial loads, torsional stress, and cumulative drag, particularly in directional or extended reach wells. For these sections, stronger grades of pipe heavier wall thicknesses and premium connections are essential. It is crucial to consider both static loads, such as the weight of the string, and dynamic loads, including torque, acceleration, and fluid drag. By designing each section individually, engineers strike a balance between efficiency and safety, thereby avoiding overdesign that would increase costs and handling complexity. This sectional approach also allows for a flexible response to changing geology and operational risks. For example, corrosive formations may require specialized pipe coatings or alloy grades in just one section of the well. Ultimately, design by hole section ensures that the drill string as a whole can meet the operational demands of the well without compromising safety or economics. The drill string is only as strong as the steel it is made from, so understanding mechanical properties is essential. Yield strength defines the point at which steel deforms permanently, while tensile strength represents the maximum load it can withstand before breaking. Toughness, or the ability to absorb energy without fracturing, is especially important under shock loading. Fatigue resistance reflects the ability of the steel to endure repeated cycles of stress, which is the most common mode of drill string failure. API specifies grades of steel with defined yield strengths, such as E75, X95, and S135. Each suited to different operational conditions. Higher strength grades allow for deeper wells and greater torque, but they may also be more brittle and less tolerant of surface damage. Temperature and environment also play key roles, as high downhole temperatures reduce steel strength, while corrosive fluids promote cracking and pitting. Understanding the stress-strain curve allows engineers to set safe operating limits that prevent overload and ensure the pipe operates well below its yield point. In practice, engineers design drill strings with conservative safety factors to accommodate both predictable loads and unexpected conditions. This balance between strength, toughness, and fatigue resistance is what ultimately keeps the string intact through complex and demanding drilling operations. Drill string failures occur when the applied stresses exceed the material or design limits, and they represent one of the most costly problems in drilling operations. Failures can be grouped into sudden overload events or gradual fatigue-related issues. Overload occurs when a pipe is subjected to stresses exceeding its yield or tensile strength, resulting in catastrophic breaks in tension, torsion, or compression. These are often the result of poor planning, incorrect calculations, or severe downhole conditions such as unexpected overpull. Fatigue failures, on the other hand, result from repeated cycles of stress, often well below the yield strength, which gradually initiate cracks that propagate until failure occurs. Common contributors to fatigue include doglegs in directional wells, high rotary speeds, and vibration. Fatigue accounts for more than half of all drill string failures, making it the most significant mechanism to address. Other mechanisms include connection wear, corrosion-assisted cracking, and handling damage on the rig floor. Each mechanism leaves characteristic signs that can be identified during inspection, such as beach marks in fatigue failures or necking in overload breaks. By understanding failure mechanisms, engineers can design more robust strings, apply proper handling procedures, and implement inspection regimes that significantly reduce the risk of costly downtime and fishing operations. Overload failures occur when the applied stresses exceed the mechanical limits of the steel. They tend to happen suddenly and without much warning, making them particularly dangerous. The most common overload mode is tensile failure, when the string is subjected to a pull greater than its tensile capacity. This often occurs during stuck pipe incidents, where operators apply excessive overpull in an attempt to free the pipe. Another frequent overload failure is torsional shear, caused by applying too much torque while drilling. This leads to twisted off connections, often seen at the weakest section of the tool joint. Compressive overload can also occur, particularly in buckled pipe, where axial loads exceed the column strength and cause permanent deformation or collapse. Overload failures are more prevalent in deeper wells where total string weights and torque requirements are higher. The key to prevention lies in proper design safety factors, accurate load calculations, and adherence to operational guidelines. Overpull should always remain below 80% of the pipe's tensile capacity, and torque should be carefully monitored, particularly in high-friction directional wells. Good operational discipline, including controlled tripping and rotation speeds, helps ensure that the drill string is not inadvertently pushed past its limits. Fatigue is the most common and insidious cause of drill string failure. Unlike overload failures, which occur instantly, fatigue develops over time through the gradual accumulation of microscopic cracks. These cracks typically initiate at surface imperfections such as scratches, corrosion pits, or stress concentrators at the thread roots of connections. Each rotation of the drill string introduces a stress cycle, and in deviated or horizontal wells, these stresses are compounded by bending in doglegs. The result is a high cycle fatigue environment that can break pipe even when loads remain well below the steel's yield strength. Beach marks and ratchet lines on failed pipe surfaces are classic indicators of fatigue. Regular non-destructive inspections, such as magnetic particle testing or ultrasonic testing, can identify early signs of fatigue before catastrophic failure occurs. Ultimately, fatigue management is about controlling cumulative damage over the life of the pipe, which requires both good design and vigilant operational practices. Other forms of fatigue are caused by corrosion, which reduces the wall thickness, altering the material properties of the steel. The third type of fatigue is H2S embrittlement, where steel exposed to H2S, which can be common in certain reservoirs, becomes more brittle due to the attack on the steel. The graph from DS1 shows the relative percentages of the different types of failure mechanisms. Fatigue is the most common. If you experience a string failure, the most likely cause is fatigue. After fatigue, torsion failures occur because when a drill string becomes stuck, the driller will pull and wrap torque into the string. Another common cause of torsional failure is from back reaming. The strength of the steel is limited under tension and reduces significantly when torque is applied. Third is exposure to H2S, causing embrittlement. There are many large reservoirs, especially in the Middle East, that have H2S dissolved in the reservoir. This requires specially enhanced steel in the drill string and tubulars to provide some mitigation to this common problem. Tensile and torsion design factors keep the applied loads within the mechanical strength of the material selected for the drill string. Normally, these factors are in the range 1.0 to 1.3 when done manually. However, DS1 identifies preordained groups where the factors and constraints are published. Design factors represent the margin of safety applied to drill string loads, reducing the risk of failure. For tensile loads, a design factor of at least 1.25 is commonly used, meaning the expected maximum load should not exceed 80% of the pipe's tensile capacity. For torsion, design factors are often more conservative, particularly in high torque wells, where a factor of 1.5 or greater may be applied. These factors account for uncertainties such as load fluctuations, measurement inaccuracies, and material variability. Fatigue design factors are more complex, as they must consider the cumulative effect of stress cycles, environmental conditions, and inspection history. DS1 provides guidance on minimum design factors, emphasizing fatigue reduction through proper planning of dogleg severity, rotary speed, and connection selection. The goal of applying design factors is to create an operational envelope that keeps stresses well within the steel's safe limits, even under unexpected conditions. While conservative design factors increase safety, they must also be balanced against cost and efficiency. An overly conservative design may lead to heavier, more expensive pipe, which increases handling difficulty and rig costs. The challenge for engineers is to strike the right balance between reliability and efficiency. Design constraints are the practical limits that engineers must respect to ensure safe operation of the drill string. Overload constraints are relatively straightforward. The pipe must never be subjected to tension, compression, or torque that approaches its rated limits once design factors are applied. This means controlling overpull during stuck pipe situations, limiting torque application during drilling, and carefully planning trip speeds to avoid excessive surge and swab pressures. Fatigue constraints are more complex, as they involve managing cumulative stresses over time. This includes limiting dogleg severity, optimizing trajectory planning, and monitoring rotary speed to reduce the number of stress cycles. Ignoring fatigue constraints often results in premature pipe failure even when overload limits are never exceeded. Corrosion and wear further tighten these constraints, reducing the pipe's capacity and fatigue life. Engineers must therefore design with both overload and fatigue in mind, recognizing that these constraints are not independent but often interact. A well-designed string respects both sets of constraints, ensuring that the pipe can operate reliably across the full range of expected conditions throughout the well's lifetime. With the exception of BSR, all other indices are defined in DS1. BSR refers to connection flexibility differences between the box and the pin. SR refers to comparisons between the stiffness of two different drill string elements, e.g. drill collar, versus the heavyweight drill pipe, and the junction between the drill collar and the heavyweight drill pipe. CI refers to a combination of dogleg severity and axial tension, which is an indicator of side loading. The numerical value of CI is inversely proportional to the fatigue crack propagation life of a drill pipe tube. SI is a quantitative measure of the relative fatigue resistance to a buckled BHA. This table illustrates how we apply design factors and constraints to evaluate both overload and fatigue in drill string and bottom hole assembly, or BHA, design. It essentially divides our considerations into two categories: overload design on the left and fatigue design on the right. Starting with the BHA structural soundness, overload design relies on simple metrics such as the load factor, the minimum overpull capacity, and the design factors for tension and torsion, abbreviated here as DFT and DFTR. These ensure that the BHA components will not fail immediately when subjected to large axial pulls or torque beyond normal operational loads. On the fatigue side, however, the assessment is more nuanced. We use the bending strength ratio, or BSR, which measures the ability of components to resist cyclic bending stresses. The stiffness ratio, SR, reflects how the relative stiffness of BHA elements influences stress distribution. The stability index, SI, is used to evaluate how the BHA resists buckling during drilling. Finally, a dedicated design factor for BHA buckling, DFBHA, is also applied. For the drill string as a whole, overload design again uses the load factor, minimum overpull, and design factors for tension and torsion. But for fatigue, the controlling metric is the curvature index, CI, which measures the ability of the pipe to tolerate repeated bending through doglegs and directional changes. This table is taken from DS1 Volume 2, which provides guidance on drill stem design and operation. What it's showing us here is the concept of design groups, which provide a structured way to decide how conservative we need to be when applying design factors and inspection criteria. There are 3 design groups, numbered 1 through 3, and each represents a different balance between cost, experience, and risk tolerance. Design Group 1 applies when the consequences of failure are low, past failure experience is minimal, and the organization has a relatively high tolerance for risk. In other words, it's suited for lower risk wells or environments where a failure, while undesirable, would not be catastrophic. Design Group 2 represents the middle ground. The costs of failure are moderate, a history of failure exists, and the organization is prepared to accept only a moderate level of risk. This category is often the default in many operations, as it strikes a balance between efficiency and reasonable caution. Design Group 3 is the most conservative. It applies when failure costs are moderate to high, there is significant past experience of failures, and the organization has little or no tolerance for risk. This group demands the strictest design factors and the most rigorous inspection criteria, which is typical of high-value or high-risk wells, such as those in deep water or HPHT operations. This table presents the design factors and constraints recommended by DS1, broken down by design group. It ties together overload design, fatigue design, and inspection requirements, showing how conservative we need to be depending on whether we are in Group 1, 2, or 3. Starting with overload design, we identified two key design factors, DFT, which encompasses tension, and DFTR, which encompasses torsion. DS1 recommends that tension factors be at least 1.25 for Group 1, 1.15 for Group 2, and 1.0 for Group 3. Torsional factors are held at 1.20 across all groups. What this means in practice is that for wells which have a high daily cost, such as deep water, we would apply design group 3 tolerances due to the higher level of inspection. The table also sets limits for load and overpull. The maximum load factor cannot exceed 100% of rated capacity, and minimum overpull is standardized at 15% across all groups. This ensures a consistent buffer for unexpected downhole conditions. Moving into fatigue design, DS1 provides constraints such as bending strength ratio BSR, stability index SI, curvature index CI, stiffness ratio SR, and BHA buckling factor DFBHA. The numbers show progressively stricter limits as you move from Group 1 to Group 3. For example, maximum SI drops from 1000 in Group 1 to just 200 in Group 3, reflecting lower tolerance for instability in high-risk operations. Finally, inspection requirements tighten as risk increases. Group 2 calls for DS1 Category 3 inspections, while Group 3 requires Category 5. Slip cut severity also becomes stricter, reducing from 10% allowable wall loss to just 5% in the highest category. In summary, this table tells us that DS1 scales design conservatism and inspection rigor depending on risk exposure, balancing safety, cost, and operational realities. In this first sub-module, we have covered the primary influences on drillstring design, reviewed the key industry references that guide our work, and discussed the mechanical properties of steel that underpin drillstring performance. We also explored the main failure mechanisms, both overload and fatigue, and examined how design factors and constraints are applied. The remaining objectives listed at the start of the module, such as advanced modeling, dynamic load analysis, and inspection methodologies, will be addressed in later sub-modules. For now, the essential goal has been to establish a strong foundation in how drill string design is influenced by forces, standards, material limits, and failure modes. With this knowledge, you are prepared to build toward more advanced applications in subsequent sessions. Thank you for your attention. This concludes the first sub-module on drill string design. We have built a solid foundation by examining influences, failures, and design principles. In the upcoming sub-modules, we will expand into more advanced topics, ensuring a comprehensive understanding of drill string performance and reliability. Please proceed to the quiz.